Paralysis might not always mean the connection is gone. In some cases, it's still there, just silent. Psychedelics and spinal cord injuries seem like they belong in completely different conversations. One is associated with altered perception and consciousness, and the other with permanent physical disability. But recent neuroscience is starting to explore a connection that is less about repairing damage and more about how the brain adapts when its normal pathways are disrupted. A spinal cord injury interrupts the flow of information between the brain and the body. Signals that once traveled freely through the spinal cord are either weakened or completely blocked. In cases of complete injury, those connections are physically severed. But in many cases, especially in complete injuries, the situation is more complex. Some nerve pathways remain intact, but they are no longer functioning effectively. They may be suppressed, disconnected, or too weak to carry meaningful signals. This is where the concept of neuroplasticity becomes central. Neuroplasticity refers to the nervous system's ability to reorganize itself by forming new neural connections. It is the same mechanism that allows people to recover function after strokes or brain injuries. The brain is not static. It can reroute signals, strengthen alternative pathways, and adapt to new conditions when given the right stimuli. Psychedelics, such as psilocybin and LSD, appear to temporarily enhance this plasticity. They primarily act on serotonin 2A receptors in the brain, which are heavily involved in cognition, perception, and neural signaling. When these receptors are activated, a cascade of downstream effects occurs. Among the most important is an increase in brain-derived neurotrophic factor, or BDNF. This molecule plays a key role in supporting neuron survival, growth, and the formation of new synaptic connections. In laboratory studies, psychedelics have been shown to increase dendritic branching, which means neurons grow more connection points. They also appear to promote synaptogenesis, the formation of new synapses where neurons communicate. In simple terms, they may place the brain into a more flexible or rewire-ready state, similar to what is seen during early development or critical learning periods. This matters in the context of spinal cord injury, because recovery is not always about restoring the original pathway. Often, it is about finding alternative routes. If some spinal pathways are still physically present, but functionally inactive, increasing the brain's ability to reorganize could help bring those pathways back into use. Instead of trying to rebuild a destroyed connection, the brain may learn to route signals through weaker or previously unused circuits. There is also a systems-level effect. Psychedelics alter how different regions of the brain communicate with each other. Under normal conditions, brain networks are relatively structured and compartmentalized. During a psychedelic state, those boundaries become less rigid. There is increased global connectivity, meaning regions that do not communicate begin interacting more freely. This may enhance the brain's ability to coordinate new patterns of activity, including those required to regain motor function. In addition, there are early indications that psychedelics may influence inflammation and glial cell activity. After a spinal cord injury, the local environment becomes hostile to regeneration. Inflammatory signals and inhibitory molecules limit the ability of neurons to regrow or reconnect. If psychedelics can reduce some of this inhibitory pressure, even modestly, they could contribute to a more favorable environment for recovery. This aspect is still speculative, but biologically plausible. Despite all of this, there are important limitations. Psychedelics do not reconnect severed spinal cords. In cases where the physical structure is completely disrupted, there is no pathway for signals to travel through, regardless of how plastic the brain becomes. This is why the current thinking does not position psychedelics as a standalone treatment. Instead, they are being considered as a potential adjunct. The most realistic model would involve combining multiple approaches. Physical rehabilitation provides repeated input to train the nervous system. Electrical stimulation can activate spinal circuits directly. Regenerative therapies aim to repair or replace damaged tissue. In this context, psychedelics could act as an amplifier, increasing the brain's responsiveness to these interventions during a limited window of heightened plasticity. The key idea is not that psychedelics fix spinal cord injuries. It is that they may help the brain do what it already has some capacity to do: adapt, reorganize, and relearn more effectively. This is particularly relevant in incomplete injuries, where the underlying structure still offers something to work with. At this stage, the evidence is still early and largely preclinical. There are no established clinical protocols using psychedelics for spinal cord injury recovery. The concept remains under investigation, and significant research is needed before any conclusions can be drawn about safety, efficacy, or practical use. What makes this area of study compelling is not the idea of a miracle cure, but the possibility of enhancing the body's own adaptive mechanisms. If the nervous system can be nudged into a more flexible state, even temporarily, it may open a window where recovery becomes more achievable than previously thought.